So let's say we have a battery here, and we want to know what happens if we connect both ends of this battery. So this positive end, this is the negative end. What happens if we connect these two ends with a wire? Well, let's look into what happens inside the wire. Well, this is my wire here. Something like this. Well, we have a negative end and a positive end. Well, the negative is fucked up a little here, but what will happen to an electron here is going to be pushed towards the positive side, and that's because of force that is caused by an electric field that's inside this wire here. It's going to push the electrons from negative to positive, and yeah, someone comes up to us and asks us, how strong will this electric field be? And they also ask us about the current flowing inside this wire, and they give us the length of this wire, which is 14.6 meters. We also know this is an AA battery, so the voltage is going to be 1.5 volts. And we also know the diameter of this wire, which is 2.5 millimeters. And they also, they ask us for the intensity. It's unknown, and they also tell us this is a copper wire. So we have a copper wire. And first of all, we want to find out what the electric field is going to be. And we can view this basically as one point which is negatively charged, and it's connected to a positive end, and it has a distance L that it's apart, and there's a difference in electric potential. And the formula for the electric field simply is the difference in electric potential over the distance itself, so that's going to be V over L. We simply plug in our numbers here into this equation, which is 1.5 volts here, by the length of the wire. It's the distance through which these two ends are apart. That's 14.6 meters. This will yield something like 0.1 volts per meter, and we can also write this as 0.1 Newton per Coulomb. And to find out what the current in this wire, in this circuit is, we can use Ohm's law. Ohm's law states that the difference in electric potential is equal to the current times the resistance. Well, we know the difference in electric potential. What's the resistance going to be? We know that the resistance is proportional. Here we know that the resistance is proportional to the length, so the longer we go, the higher the resistance is going to get. We also know that the resistance is inversely proportional to the cross-sectional area of a wire. That means if we have a thicker wire, there's going to be less resistance. If we have a thinner wire, there's going to be higher resistance. So it's 1 over the cross-sectional area. We combine these two, we get proportional to length over the area. And to make this into an equal sign, we need a proportionality constant. That will give us an equation that looks like this. It's equal to rho. This here is the proportionality constant times L over A, and we know rho is material dependent, and for copper we have a rho, or a resistivity, of 1.68 times 10 to the negative 8 ohm meter. And we can plug in this into our Ohm's law, and that will yield an equation that looks like this, times rho L over, and we know the cross-sectional area is going to be pi r squared. We do some algebra, we end up with an equation that looks like this. Rho L is going to be equal to current. We plug in all the values and we will get a current of 30 ampere.